All right, get ready, because today we're going on a deep dive.
A deep dive.
Yeah, into the atom.
That's good.
But, everyone knows the basics about atoms, so we're going beyond that.
Absolutely. Yeah.
We're going deep, deep, deep.
Deeper than the textbook.
Deeper than the textbook, exactly.
Love it.
So think of this as, I guess you could say Atom 101.
Okay.
But like way more engaging
Yeah.
than just reading a textbook, right?
Definitely.
So let's start with something I think everyone has experienced at some point.
Mhm.
Static electricity.
Okay.
Like, you walk across the carpet
Yeah.
and you touch a doorknob.
And a zap.
Yeah.
Exactly.
Ain't it been there?
Or like maybe a balloon sticking to your hair after you rub it.
Oh, yeah, classic.
Yeah, it's a classic.
That's a good one.
So, I mean, it's a pretty simple thing, right? But it hints at something much bigger.
Yeah, it really does.
It hints at the fact that there are these charged particles
Mhm.
that exist within matter.
Yeah.
Within matter. Yeah. So it's like one of those first clues that,
Right.
atoms might not be as simple as we initially thought,
Oh, interesting.
This idea of them being indivisible.
Right.
Like maybe there's more going on inside.
More than meets the eye, right?
Yeah, exactly.
So these simple observations about static electricity, I mean, it kind of sparked the scientific curiosity
Yeah,
to figure out, well, what is going on inside an atom?
absolutely. And that led to so many discoveries, really revolutionized our understanding of matter.
Okay, I am intrigued.
Good.
Let's dive into those discoveries then.
All right.
Where do we start?
Let's start with one of the earliest breakthroughs, I would say.
Okay.
The electron.
Oh, the
A
electron.
tiny little particle
Yeah.
with a negative charge.
Okay.
And it's a fundamental part of every single atom.
Every single atom.
Okay.
I remember learning about these back in school.
Yeah.
So who was it that figured out that these tiny particles were in there?
Well, we can thank J.J. Thomson for that one,
Oh,
brilliant
good.
physicist.
Okay.
And he came up with a model of the atom
Okay.
that, it was pretty imaginative. It was called the plum pudding model.
Plum pudding.
Plum pudding.
That's a name that makes you hungry,
Yeah, right.
Tell me more about this delicious sounding model.
Okay, so imagine a plum pudding, right?
Okay.
The pudding itself
Okay.
represents a positively charged sphere,
Okay.
and the plums that are scattered throughout,
Yeah.
those are the negatively charged electrons.
Okay.
So essentially, he's envisioning the atom as this positively charged
Blob.
blob, yeah, with these electrons just embedded within it.
Kind of like raisins in a cake.
Yeah, you could think of it that way, yeah.
I mean, that kind of makes sense, right? You have the
Right.
positive and the negative charges
Right.
balancing each other out, so the atom is electrically neutral overall.
Exactly.
Makes sense.
Yeah.
And this was a pretty big deal at the time, right?
Oh, huge.
Because it was the first model to suggest that atoms weren't just these solid, indivisible spheres, but that they actually had an internal structure.
Yeah, something going on inside.
Something going on inside, okay?
It's not just a boring sphere.
Not just a boring sphere.
There's layers to this.
Layers to this. Okay,
Yeah.
so to recap, the electron,
Yeah.
which is a negatively charged subatomic particle,
Yes.
is a fundamental component of all atoms.
All atoms, that's right.
Okay, so if this plum pudding model was so revolutionary, I mean, what happened next?
Well, like many scientific theories,
Yeah.
it had its limitations.
Okay, it couldn't fully explain the results of all the later experiments.
Yeah,
And science is all about refining and refining our understanding.
absolutely. It's a constantly evolving process.
So what were those experiments that kind of shook things up?
Let's talk about Ernest Rutherford
Okay.
and his famous gold foil experiment,
Okay.
one of the most iconic experiments in the history of physics.
This is the one where they shot particles
Yes.
at gold.
Right. Right.
I'm remembering, bits and pieces from school.
Yeah.
But refresh my memory.
Okay, so Rutherford and his team
Okay.
fired alpha particles,
Of particles.
which are basically positively charged helium ions
Oh, okay.
at a very, very thin sheet
Right.
of gold foil.
Gold foil. Okay.
And they were doing this because, based on the plum pudding model,
Okay.
they expected, most of these particles to just pass straight through
Yeah.
with maybe some minor deflection.
Yeah, I could see that.
Yeah.
If the atom was this, diffuse cloud of positive charge,
Right.
it wouldn't encounter much resistance.
Yeah, it'd be like shooting through,
Right.
empty space almost.
Exactly.
But here's the thing.
Okay.
What they actually observed
Okay.
completely contradicted those expectations.
Oh, no.
Yeah.
Did they all go straight through?
Most of them did, yes,
Right.
but a small fraction.
Were deflected at significant angles.
Mm-hmm.
And even crazier,
Okay.
a tiny number of them
Yeah.
bounced straight back.
Wait, hold on. Bounce straight back.
Straight back.
Like they hit a wall?
Yeah, basically.
That doesn't sound like a diffuse plum pudding at all.
No, it doesn't.
That's crazy.
It was a shocking result.
Yeah.
Like, imagine
Yeah.
shooting a cannonball at tissue paper
Mm-hmm.
and having it ricochet back at you.
Wow. Okay.
Yeah, that's basically what happened.
So, I mean, they must have hit something
Right.
incredibly small and dense
Immense, yeah.
within the atom.
Within the atom.
Something much more substantial
Yeah,
than what that plum pudding model suggested.
exactly.
So what was it?
Well, Rutherford, being the brilliant scientist that he was,
Yeah.
he deduced that the atom
Okay.
must have this tiny, positively charged
Okay.
nucleus
Nucleus.
right at its center,
Okay.
where most of its mass is concentrated.
Okay, so that's why some of those alpha particles
Going-
experienced such a strong repulsive force
Uh-huh.
and were deflected
Yeah.
or bounced back.
They hit that nucleus.
They hit that nucleus, okay?
Yeah.
So, goodbye plum pudding.
Right.
Hello nucleus.
Hello, nucleus?
This experiment really changed our whole understanding of the atom.
Big time.
So to recap, Rutherford's gold foil experiment demonstrated that atoms have a small, dense, positively charged nucleus at their center, right?
That's right.
Okay.
Challenging that plum pudding model.
Yeah,
And leading to a new era
a new era.
of atomic understanding.
So we have the electron, we
Mhm.
have the nucleus.
Yes.
I feel like there's another player
Mm.
in this whole atomic game.
Oh, there is, yeah.
What about the proton?
Ah, yes, the proton.
Yeah.
It actually entered the scene a bit earlier, thanks to E. Goldstein.
Okay,
Yeah.
I don't remember him.
Yeah. He discovered something called canal rays.
Canal rays.
These are positively charged radiations. Okay.
That basically led to the identification of the proton.
Okay, so the proton is like the counterbalance to the electron,
Yes, exactly.
but it's in the nucleus.
in the nucleus.
Not just, flying around.
Yeah, it's got different roles.
What's the deal with it being so much heavier
That's a good question.
than the electron?
It is, yeah. So the proton is about 1,836 times
Wow, okay. Okay.
more massive than the electron.
Oh, wow.
Yeah, they have equal but opposite charges, right?
Okay.
But the masses are vastly different.
Just to recap, the proton
Yeah.
is a positively charged subatomic particle
Yes,
found in the nucleus
that's right.
of an atom,
Uh-huh.
and it's got a way bigger mass
Way bigger
than an electron.
than the electron, yeah.
Okay, so we've got these electrons, which are negatively charged,
Right.
buzzing around the nucleus,
Yeah.
which contains protons, which are positively charged.
Yeah.
It's starting to feel like a real atom. Is that all there is to it, though?
Well, we're getting closer.
But there's one more crucial piece
No.
to add to our atomic puzzle.
Okay.
And this one was a bit of a late bloomer.
Ooh, a late bloomer.
Yeah.
I'm sensing a good story here.
There is a good story.
Yeah.
It involves some clever experiments and deductions.
Okay.
But to get to the point, in 1932,
Okay.
James Chadwick
Discovered
discovered the neutron.
the neutron, okay?
Yeah.
A neutral particle residing in the nucleus.
Alongside the proton.
So no charge at all.
No charge.
What's its role in all of this?
Well, it's not just there to make things more complicated.
Right.
It actually plays a critical role
Okay.
in stabilizing the nucleus.
Right.
Remember all those protons?
Yeah, positive charge.
Positive charge all crammed together.
Yeah,
They should be repelling each other like crazy.
makes sense.
But the presence of those neutrons
Okay.
helps to offset that repulsion and hold the nucleus together.
Wow, that's pretty clever.
It is, right?
Like a cosmic glue holding those protons in check.
Yeah. I like that analogy.
So to recap,
Yeah.
the neutron
Yeah.
is a neutral subatomic particle
Yep.
found in the nucleus
That's right.
of an atom,
Yep.
and it plays a key role in stabilizing the nucleus.
Exactly.
Okay, so now we have our three main subatomic particles,
We do.
electron, proton, and neutron.
That's right. The building blocks.
Wow. We've come a long way from static electricity to all of this.
Yeah, we have.
I have a feeling this is just the beginning of our atomic journey.
You have a feeling. I know it is.
I know it is.
Yeah.
Okay, so now that we have these basic pieces,
Yeah.
let's see how they all fit together
Right.
and create the incredible diversity of elements
Right.
that make up our world.
Let's do it. So we've met the key players, right?
Right.
Electrons, protons, neutrons.
Yeah.
But it's not just about those individual properties. It's
Mhm.
about how they're all arranged.
Okay.
Yeah.
Especially those electrons, buzzing around.
Right. We left off with those negatively charged electrons just zipping around the nucleus.
Yeah.
Is there a method to this madness?
There is, yeah.
Yeah.
It's far from random,
Right.
Electrons are very organized.
Okay.
They occupy very specific
Okay.
energy levels or shells
Okay.
around the nucleus.
So kind of like concentric circles.
Yeah, think of it like concentric circles around the nucleus.
Okay, I'm picturing these electron shells.
Okay.
But how do they fill up?
Well, there are rules, of course.
Okay.
The number of electrons each shell can hold
Uh-huh.
is determined by a formula.
Okay.
It's 2n millins,
Okay.
where n is the shell number.
Okay, so the first shell
Yes.
closest to the nucleus
Yes.
can hold a maximum of 2 electrons.
That's right.
Okay.
And then the second shell can hold up to 8.
Okay.
The third shell up to 18, and so on.
Oh, interesting.
Yeah.
So the further out you go from the nucleus, the more electrons it can handle.
Yeah, exactly. The shells get bigger.
Yep.
Well, they can accommodate more electrons.
But do electrons just fill up these shells all willy-nilly?
Not at all.
Okay.
There's a pattern.
Okay.
They fill up in a very stepwise manner,
Okay.
starting from the innermost shell and then moving outward.
Okay, like building a house.
Exactly.
You start with the foundation,
Yeah,
and then you add the walls, and then the roof, you don't start with the attic.
exactly. You got it.
Okay, so each shell gets its full set of electrons
Right.
before moving on to the next.
Yeah.
Okay, but why is this electron arrangement so important?
Good question.
Like, how does it affect the way elements actually behave?
Well, it all comes down to
Okay.
the outermost shell,
Okay.
often called the valence shell.
The valence shell.
Yeah, and the electrons in this shell
Mm.
are called the valence electrons,
Right.
and these are the ones that are responsible
Okay.
for an element's chemical personality.
Okay, valence electrons, they sound important.
They are.
What makes them so special?
Well, atoms have this, yeah.
Strong desire for stability.
Okay.
And for many elements, that means having a full outer shell of electrons.
Okay.
What we call the octet rule.
The octet rule, okay.
They want 8 valence electrons.
Okay, the octet rule. 8 electrons to rule them all.
Exactly. I love it.
So it's like this cosmic game of musical chairs.
Yeah.
And the atoms are trying to grab a seat in that outer shell
Yeah.
to achieve stability.
To be stable. Exactly.
And this desire for a full outer shell is
Yeah.
what leads to all this
yes.
chemical bonding.
Chemical bonding. Yeah.
Okay, so they're sharing or gaining or losing electrons
Yeah.
to achieve that octet.
Exactly. That's what it's all about.
Okay, so it's all about those valence electrons kind of wheeling and dealing
Yeah.
to fill up those empty slots
Yeah.
in that outer shell.
It's like a marketplace.
And this is what leads to the formation of molecules and compounds and, all the amazing chemical reactions we see.
Absolutely.
It all goes back to this. It does, yeah, it's the foundation of chemistry.
So the number of electrons an atom needs to gain or lose or share
Yeah.
to complete its octet,
Uh-huh.
that's called its valency.
Valency.
I remember that term from chemistry class.
Yeah.
So chlorine, which is 1 electron shy of a full outer shell,
Yeah.
it has a valency of 1 because it just wants that 1 electron.
Exactly. It's very reactive.
Yeah.
It wants that electron.
And oxygen, which needs 2,
Right.
has a valency of 2.
That's right.
Okay, so valency is basically
Yeah.
a measure of an atom's bonding capacity.
Yeah.
And it's all dictated by those valence electrons and their quest
Exactly.
for a full outer shell.
A full outer shell. That's the goal.
So to sum up, valency is the combining capacity of an atom, determined by the number of electrons it needs to gain, lose, or share to achieve a stable electron configuration, typically a full outer shell.
Perfect. That's a great definition.
Okay, so let's not forget about those other subatomic particles,
Mm-hmm.
the protons and neutrons.
Yeah.
They're in the nucleus.
They're hanging out in there.
They play a key role in,
They do.
defining an element's identity.
Yeah.
So we talked about protons earlier
We did.
and how they determine an element's atomic number.
Right.
Can you explain that a little bit more?
Yeah. So the atomic number,
Okay.
it's like an atom's fingerprint.
Okay.
It's the number of protons in the nucleus,
Okay.
and it defines what element that atom is.
Right. So hydrogen has 1 proton.
Yep.
So its atomic number is 1.
Exactly.
Carbon has 6. So its atomic number is 6.
That's right. Simple as that.
The atomic number is like a roll call for the elements.
I like that.
Each element has its own number.
Its own designated number.
Okay. So to put it simply, the atomic number, represented by the symbol Z, is the number of protons found in the nucleus of an atom. It is a fundamental property that defines the identity of an element.
Exactly. Couldn't have said it better myself.
But what about those neutrons?
Mm-hmm.
I mean, they don't have a charge. So they don't affect the overall charge of the atom,
No, they don't.
but they do add mass.
Right. They do add mass.
Right,
So
yeah.
protons and neutrons together,
Uh-huh.
we call them nucleons,
Nucleons.
they contribute almost all of an atom's mass.
Okay.
Those electrons are so tiny,
Right.
their mass is practically negligible.
So when we talk about the mass of an atom,
Yeah,
we use the mass number,
that's right.
which is the total number of protons and neutrons
Protons and neutrons, yeah.
in the nucleus.
In the nucleus, exactly.
So like carbon,
Yeah.
6 protons and 6 neutrons.
Uh-huh.
So its atomic number is 6.
Right.
And its mass number is 12.
12, you got it.
Okay. So to put it
Yeah.
simply, the mass number represented by the symbol A of an atom is the total number of protons and neutrons in its nucleus. It gives an indication of the atom's mass.
Exactly.
Okay, so atomic number is all about protons.
Yes,
And mass number considers both protons and neutrons.
that's right.
Okay, I have a question. If the mass number is based on the number of protons and neutrons,
Yeah.
wouldn't all atoms of the same element always have the same mass number?
Ah, that's where things get interesting.
Okay.
That brings us to the concept of isotopes.
Isotopes.
Yeah.
I've heard that word before,
Yeah.
but I'm a little fuzzy on what it actually means.
So isotopes are atoms
Okay.
of the same element
Okay.
that have the same atomic number.
Same number of protons.
Same number of protons, but they have a different number of neutrons.
Wait, so you can have different versions of the same element.
You can, yeah.
That's like having different models of the same car.
Exactly. That's a great analogy.
Same basic design, but maybe one has a bigger engine.
Yeah, different features.
Okay.
So think about carbon, for example.
Okay.
The most common isotope of carbon is carbon-12,
Okay.
which has 6 protons and 6 neutrons.
Right, giving it a mass number of 12.
12, but then there's also carbon-14,
Okay.
which is a radioactive isotope of carbon.
Mm-hmm.
It has 6 protons, but 8 neutrons.
Giving it a mass number of 14.
14, so same element, different mass.
So to simplify, isotopes are atoms of the same element that share the same atomic number but have different mass numbers due to varying numbers of neutrons in their nuclei.
Right.
Perfectly said.
Okay, so isotopes are like siblings.
I like that.
They share the same atomic number, but maybe they have slightly different weights.
Yeah, some are a little heavier than others.
But why should we care about these differences?
Well,
Do they affect how elements behave?
they do. So isotopes of an element,
Okay.
they all have the same chemical properties
Oh.
because they have the same number of electrons, right?
Okay.
It's those electrons that are driving those chemical interactions,
Okay.
but their physical properties can be different.
Oh.
Things like density, radioactivity,
Okay.
even slight variations in melting and boiling points.
Okay, so even though they're like family members,
Yeah.
those extra neutrons
Yeah.
can give isotopes distinct characteristics.
Yeah.
Exactly.
Okay, so how do we account for these variations in mass
Okay.
when we talk about the atomic mass of an element
Yeah, that's a good question.
as a whole?
So that's where the concept of average atomic mass comes in.
Okay.
Since many elements exist as a mixture of isotopes in nature,
Okay.
we have to calculate the average atomic mass,
Oh.
taking into account the relative abundance of each isotope.
It's like a weighted average, considering how common each isotope is.
Exactly, a weighted average.
Okay, so that makes sense.
Yeah.
To put it simply, the average atomic mass of an element is the weighted average of the masses of its naturally occurring isotopes, taking into account their relative abundances.
Yes, that's it.
So when you see the atomic mass on a periodic table,
Uh-huh.
it's usually this average atomic mass.
That's right.
Okay.
But there's another related concept
Okay.
I want to introduce.
Okay.
Isobars.
Isobars. Okay, how are these related to isotopes?
They are related, but with a twist.
Okay.
So isobars are atoms of different elements. So they have different atomic numbers,
Okay, different number of protons.
different number of protons,
Okay.
but they share the same mass number.
Oh, interesting.
So unlike isotopes, which are like siblings in the same element family,
Okay.
isobars are like friends from different families
Oh.
who happen to have the same weight.
So they have different numbers of protons,
Yeah,
but the same total number of nucleons.
exactly.
Okay, can you give me an example?
Sure. So calcium
Okay.
with an atomic number of 20
20. Okay.
and argon with an atomic number of 18.
18. Okay.
Both have an isotope with a mass number of 40.
Okay.
So they have different numbers of protons,
Right.
but the same total number of protons and neutrons combined.
So to define an isobar, it is an atom that has the same mass number as another atom of a different element. This means they have the same total number of protons and neutrons, but differ in the number of protons in their nuclei.
Yes, that's it.
Okay, so those are isobars,
Isobars?
same mass number, different atomic numbers.
That's right.
It's amazing how these small variations
Yeah.
in the number of subatomic particles
Yeah.
can create such a huge diversity
Incredible.
in the world of atoms.
Yeah.
But I feel like we're just scratching the surface.
Oh, we are. There's so much more to explore.
Wow, from static electricity sparks
Yeah.
to this intricate dance of electrons, protons, and neutrons.
It's amazing.
It's pretty amazing what we've uncovered
It is.
about the atom.
Yeah.
But I bet there's still so much more to explore.
Oh, absolutely.
I mean, this is
Yeah, we're just getting started.
just getting spewed, really.
Yeah.
Because our understanding of the atom has come a long way, you know?
It has, yeah, from those,
Right.
early models of plum pudding
Yeah, plum pudding.
and miniature solar systems.
Yeah.
It's come a long way.
And it's really revolutionized so many fields, hasn't it?
Oh, it has, yeah. I mean, from medicine to energy, material science.
It's mind-boggling to
Yeah.
think that something so tiny, so small,
Right.
can have such a massive impact
Huge impact.
on our world.
Absolutely.
I mean, it just highlights the
Yeah.
interconnectedness of everything, right?
It does. Yeah.
Like understanding the atom allows us to understand the elements, the molecules they form.
And ultimately, all the matter in the universe.
Right, and that's everything.
It is, yeah.
So as we wrap up our atomic adventure,
Yeah.
what are the key takeaways?
Okay, key takeaways.
What should we carry with us?
So, first and foremost,
Okay.
remember that the atom,
Yeah,
once thought to be indivisible,
right?
is a complex structure
Okay.
with that positively charged nucleus at its core
Right.
and negatively charged electrons whizzing around in specific energy levels.
It's kind of like a bustling city,
Yeah.
like with the nucleus as the central hub
Yeah.
and the electrons as the commuters,
Like
following their designated route.
going their routes. Yeah.
Okay, and within that nucleus,
Mhm.
we have the protons, which determine the element's identity,
Right.
and the neutrons,
Yeah.
which contribute to the atom's mass.
Huh.
And together, they shape the atom's properties
Which you.
and how it interacts
But
with the
it's-
world.
Yeah.
And then let's not forget about isotopes.
Oh, yeah.
The isotopes.
Those variations within an element with
Yeah.
the same number of protons but different numbers of neutrons.
Different neutrons.
I mean,
Yeah.
those subtle differences can have a
Yeah.
big impact on an atom's physical properties.
They can, like radioactivity.
Right.
Exactly.
And those isotopes have proven to be incredibly valuable.
Yeah.
I mean, from their use in nuclear medicine
Mm-hmm.
and dating ancient artifacts
Right.
to their role as tracers
Yes.
in biological and chemical research.
It's like nature has given us these
Yeah.
atomic tools
Yeah.
with a vast array of applications.
So to bring it all together, remember the driving force
Yeah.
behind so much of the atom's behavior, the octet rule,
The octet rule. Yes.
that yearning for a full outer shell of electrons.
Yeah, it's like the ultimate quest
It's like, yeah,
for stability.
for atomic stability,
Right.
dictating how atoms bond,
Right.
form molecules, and ultimately shape
Yes.
the chemistry of our world,
The chemistry of everything.
right? So it's all driven by that.
Yeah. It's amazing.
So it's a truly remarkable story, isn't it?
It is.
From
Yeah.
simple observations like static electricity
Uh-huh.
to those sophisticated experiments
Yeah.
like Rutherford's gold foil experiment.
Right.
We've come a long way in understanding the atom.
We have.
And who knows
Yeah.
what further discoveries
Well,
and insights await us
Who knows what the future holds?
as we continue to explore this subatomic realm.
Yeah.
Perhaps we'll unravel even deeper mysteries
Maybe.
about the fundamental nature of matter,
Absolutely.
leading to even more groundbreaking applications.
Yeah.
That's the beauty of science, isn't it?
It is, yeah. There's always more to learn.
Always more to learn.
More to explore, more to understand.
And with our ever-evolving tools and techniques,
Yeah.
who knows what incredible secrets of the atom
Oh.
we'll unlock next.
Yeah.
So to our listener,
Yeah.
we encourage you to keep that spark of curiosity alive,
Absolutely.
to delve deeper
Yeah.
into the world around you,
Keep asking questions.
and to never stop asking questions.
Yeah.
After all, it's that insatiable thirst for knowledge
Uh-huh.
that has driven us
Yeah.
to uncover these amazing secrets of the atom.
Absolutely.
And it's that same spirit
Yeah.
that will continue to propel us forward
Yeah.
on this endless journey of discovery.
It's a journey, that's for sure.
So until next time,
Yes.
Keep diving deep.
Keep diving deep.